Alright, hey everyone, welcome back to 3 Deviations. In today's video, we want to keep looking at elementary series. Today we want to look at infinite telescoping series. That sounds kind of weird, but I promise you'll understand by the time this is over. This is not a geometric series, but it is a nice series in that it is still one that we can calculate the sum of if it is convergent. And it's a little bit tricky how we do the sum. We just need to bring back a lot of algebraic techniques that we learned in pre-calculus and also in Unit 6 when we were talking about integration techniques, i.e. partial fractions. So it's important that we kind of harken back to that, but it shouldn't be too bad. So telescoping series are, a little bit tedious, and they're really when we're involving kind of a fraction. We know the series converges, that's how we're going to find the sum. But they're usually rational. They look rational. So you have a function over a function, or you just have 1 over a function, or a polynomial over a polynomial. Okay, so we're just going to do an example. So it's hard to describe this really abstractly, so we're just going to explain it through an example. This isn't a super important topic, it's just a series that you might see on your test. So the series that we want to look at today is the sum from n equals 1 to infinity of 1 over n plus 1 times n plus 2. So I did the factoring work for you, so you're welcome. Anyways, what we want to do is we want to first make sure that this is convergent. So we are going to take the limit. We're going to use the test for divergence. So if you remember, that means we're taking the limit as n approaches infinity of a sub n. So if this were a sequence, we're just making sure that the infinite term isn't infinity or something like that. So you get 1 over n plus 1 times n plus 2. And it should be obvious that this is going to converge because this limit's going to be 0, right? There's nothing in our numerator other than 1. So if we keep adding, if we go to 1 over infinity, we're going to be converging. So we have a convergent series here. And also what's important to note is that we are of order n squared in the denominator. If we were of order n, then we'd have a little bit of a problem because that would be kind of a derivative of what we call a harmonic series, or I guess not a derivative. You got to be really careful with what you say, like a tributary of the harmonic series, which we'll talk about in the next video, and that's something that does not converge. But we are of order 2, so we're fine. Okay, so what we want to do now is we want to make this a little bit easier to deal with. We want to make what's inside the limit easier to deal with. So in order to do that, we are going to make a partial fraction decomposition. You're going to see exactly why we do this. So if we do a partial fraction decomposition, we want our linear factors to be separate. So we get 1 over n plus 1 times n plus 2 is equal to a over n plus 1 plus b over n plus 2. Okay, so we can multiply everything by the lowest common denominator. Then we get 1 is equal to a times n minus 1 plus b times n minus 2. Now, luckily, this is easy enough for us to deal with this with the cover-up method. So we can just set n equal to -2 to 0 the b term, and that will give us b equals -1. And then we can 0 the a term, or then we can 0 the b term, and we get a is equal to 1. So we get -1 and 1 for each of our terms. Okay, so this gives us a partial sum. So our partial sum of our series is going to be equal to 1 over n plus 1 minus 1 over n plus 2. So note that n now has a slightly different role than it did in the series. It's no longer the index. Okay, so what we would like to do now is we are just going to simply expand this. So we're going to write this for all n, and we're going to make a nice dot, dot, dot in the middle. So if we do the first term, n will be equal to 1. So that's 1/2 minus 1/3. So then we're going to add the second term. So that's when n is equal to 2. So we get 1/3 minus 1/4. And then we'll do the same with the third term. So we get 1/4 minus a fifth. And then we keep on going, and then we're going to get to some point where we're at 1 over n minus 1 over n plus 1, and then we have the last term, 1 over n plus 1 minus 1 over n plus 2. Okay, now the reason that we did all of this partial fraction shenanigan was so that we could get to the point where we have this expression, because with this expression we get something really nice. If you'll notice, with the exception of the very first term and the very last term, all of these terms have a negative of themselves somewhere in the expression. Even the ones we can't see in the dot, dot, dot. Those behave just like the ones we can't see. So we see this negative 1/3 and we see the positive 1/3. Well, those guys are going to cancel out. We see the negative 1/4 and the positive 1/4. Well, those guys are going to cancel out as well. The 1/5 and some 1/5 in the next term is going to cancel out, and then all the things in the middle are going to cancel out. And we're going to get to the point where we're at 1 over n. There's going to be a negative 1 over n the term before that, so that cancels out. N plus 1s cancel out, and then we're just left with the 1/2 and the negative 1 over n plus 2. So that's why we decomposed it to the partial fraction, so that we could expand, get this nice expression. We can cancel out almost everything, but we're left with something finite. We're left with this 1/2 minus 1 over n plus 2, something that's going to be easy to deal with. And if I want to take the infinite sum, well, that's just going to be the limit as n approaches infinity of this expression, 1/2 minus 1 over n plus 2. Well, we can pull the 1/2 out of the limit immediately, but also this guy is going to go to 0 because 1 over infinity is 0. So we're going to get 1/2. So that is how you deal with a telescoping series. And they kind of call it telescoping because you're going to get, like, if you graph it, you'll get, it's not like exactly alternating, but it looks kind of like it's alternating. Like you get that, then it gets bigger, then it gets bigger, but you keep getting like you get the negative of each term, and it ends up being nice. And then you get something where all of these cancel out, and then you get that term and then the last term. And then you can add those together. There you go. So that's how the telescoping series works. In the next video, we're going to start talking about the integral test. It's our first main test for divergence, other than the test for divergence that we covered, which is what we did up here. And that will lead us to a proof on why the harmonic series is divergent. Okay, we'll see you then. Bye.